Dear friends, have a good day. Here in this video today we are going to look at the topic complex integration. In this complex integration, today we are going to look at zeros, singularities and residues of an analytic function. Here we go. First off, zeros of an analytic function. What is zeros of an analytic function? If a function f of z is analytic in a region R is 0 at a point z is equal to z0 in R, then z0 is called a 0 of f of z. That is, 0 of an analytic function f of z is defined as if we put z is equal to z0 in f of z, it will become 0. Then the point z is equal to z0 is called the 0 of an analytic function f of z. There are two types of 0, that is simple 0, another one is 0 of order n. What is simple 0? If f of z0 is equal to 0 and f dash of z0 not equal to 0, then z is equal to z0 is called a simple 0 of f of z or a 0 of first order. On the other hand, if f of z0 is equal to f dash of z0 is equal to etc is equal to fn minus 1 dash of z0 is equal to 0 and fn dash of z0 not equal to 0, then the point z0 is called 0 of order n. Have a look at this point. An analytic function f of z is said to have a 0 of order n if f of z can be expressed as f of z is equal to z minus z0 whole power m into phi of z, where phi of z is analytic and phi of z0 not equal to 0. That is, if the analytic function has a zeros of order n, then the f of z can be expressed as f of z is equal to z minus z0 whole power m into phi of z, where the phi of z must be analytic and phi of z0 must be not equal to 0. Now we are going to look at a singularity of an analytic function. What is mean by singularity? A point z is equal to z0 at which a function f of z fails to be analytic is called a singular point or singularity of f of z. That is, if the function f of z is analytic everywhere except at a point z is equal to z0, then the point z is equal to z0 is called the singular point. Say for example, consider the function f of z is equal to 1 by z minus 3. In this function, if we put z is equal to 3, then what you will get is f of z is equal to 1 by 0, it will become infinity. So we cannot define the function f of z at a point z is equal to 3. So that is why the point z is equal to 3 is called a singular point. There are two types of singularity. One is isolated singularity, another one is non-isolated singularity. What is isolated singularity? A point z is equal to z0 is said to be isolated singularity of f of z if f of z is analytic everywhere except at a point z is equal to z0. That is, the function is analytic everywhere, but at a particular point z is equal to z0, the function f of z fails to satisfy the analyticity. So that is why the point z is equal to z0 is called isolated singular points. What is non-isolated singular point? If f of z is not analytic at two or more points of z, then f of z is said to have non-isolated singular points. Because it has two or more singular points, then it is called non-isolated singular points. Now we are going to look at the type of isolated singularity. There are three types of isolated singularity. One is removable singularity, another one is poles, another one is essential singularity. Here, essential singularity comes under both the category isolated singularity and a non-isolated singularity. Now we are going to look at what is removable singularity. If z is equal to z0 is an isolated singular point of a function f of z, then the singularity is called a removable singularity. If the Lorentz series expansion about z is equal to z0 has no negative powers of z, that is, sometimes we called the isolated singular points are called removable singular points. When isolated singular points are said to be removable singular points, if the Lorentz series expansion contains no negative powers of z, then the isolated singular points are called removable singular points. That is why this singularity is called removable singularity. And then poles. What is poles? If z is equal to z0 is an isolated singular points of a function f of z, then the singularity is called pole. If the Lorentz series about z is equal to z0 of f of z has a finite number of negative powers of z, that is, sometimes the isolated singular points are called pole. When isolated singular points are called poled means if the Lorentz series expansion of f of z contains finite number of negative powers of z, then the isolated singular points are called pole. Now we are going to look at essential singularity. If z is equal to z0 is an isolated singular points of a function f of z, then the singularity is called an essential singularity. If the Lorentz series expansion of f of z about z is equal to z0 has infinite number of negative powers of z, that means sometimes the isolated singular points are called essential singularity. When the isolated singular points are called essential singularity, if the Lorentz series expansion of f of z contains infinite number of negative powers of z, then the isolated singular points are said to be essential singularity. Isolated singularity. This is the clear definition of isolated singularity. A point z is equal to z0 is said to be isolated singularity of f of z if f of z is not analytic at a point z is equal to z0 and there exists a neighborhood of z is equal to z0 containing no other singularity, which means that the function f of z is not analytic at a particular point z is equal to z0, but in the deleted neighborhood of z0 the function f of z is analytic. For example, the function f of z is equal to 1 by z is analytic everywhere except at the point z is equal to 0. Therefore, z is equal to 0 is an isolated singularity, because if we put z is equal to 0 in the function f of z, then what you will get is 1 by 0, it will become infinity. So we cannot define the function f of z at a particular point z is equal to 0. Therefore, this type of singularity is called isolated singularity. Note: let z is equal to z0 be an isolated singular point of the function f of z, then f of z is analytic inside and on a circle C except at z is equal to z0, which is the center of the circle C, and therefore f of z can be expanded by the Lorentz series f of z is equal to summation n is equal to 0 to infinity a n into z minus z0 whole power n plus summation n is equal to 0 to infinity b n by z minus z0 whole power n. So this is the expansion of f of z when z is equal to z0 is an isolated singular points. Now we are going to look at removable singularity. If the principal part of f of z contains no term, that is, if bn is equal to 0 for all n, then the singularity z is equal to z0 is known as the removable singularity of f of z, which means that the principal part does not contains any negative powers of z, because if it is 0 then it does not contain any negative powers of z. That is why these isolated singular points are called removable singularity. Therefore, f of z becomes summation n is equal to 0 to infinity a n into z minus z0 whole power n. A singular point z is equal to z0 is called a removable singularity of f of z if limit z tends to z0 f of z exists finitely. How do you check whether the given function has a removable singularity? If we take limit z tends to z0 of f of z, if we get a finite value, then the singular point is called removable singularity. Now we are going to look at pole. If it is possible to find the positive integer n such that limit z tends to a z minus a whole power n into f of z not equal to 0, then the z is equal to 0 is called a pole of order n for f of z. Simple pole. If the pole of order is 1, then the pole is called a simple pole. Now we are going to look at essential singularity. If the principal part contains an infinite number of non-zero terms, then z equal to z naught is known as essential singularity. That means that in the Lorentz series expansion, if the principal part contain an infinite number of negative powers of z, then the isolated singular points are called essential singular points. For example, f of z is equal to e power 1 by z. If we expand this with the help of exponential series, then what you will get is 1 plus 1 by z by 1 factorial plus 1 by z whole squared by 2 factorial plus 1 by z whole cube by 3 factorial plus etc. That is, we have 1 plus 1 by z can be written as z power minus 1. So we have 1 plus z power minus 1 by 1 factorial plus z power minus 2 by 2 factorial plus z power minus 3 by 3 factorial plus etc. In this series, it contains infinite number of negative powers of z. That is why z is equal to 0 as an essential singular points. Keep this thing in mind. The removable singularity and the poles are isolated singularity, but the essential singularity is either comes under isolated singularity or non-isolated singularity. And then meromorphic function. When a function is said to be meromorphic function, a function f of z which is analytic everywhere in the finite plane except at a finite number of poles, then the function is called meromorphic function. For example, f of z is equal to z plus 3 divided by z minus 1 into z minus 2 whole squared. This is called a meromorphic function since it fails to be analytic at the poles z is equal to 2 and z is equal to 1. That is why this function is called meromorphic function. Now we are going to look at residue of an analytic function. What is a residue of an analytic function? If z is equal to z naught is an isolated singular point of f of z, we can find the Lorentz series of f of z about z is equal to z naught is f of z is equal to summation n is equal to 0 to infinity a n into z minus z naught whole power n plus summation n is equal to 0 to infinity b n by z minus z naught whole power n. In this Lorentz series expansion, the coefficient of 1 by z minus z naught is called the residue of an analytic function. Here the coefficient of 1 by z minus z naught in the expansion is called the residue of f of z at z is equal to z naught. Therefore, here b1 is the residue of f of z at z is equal to z naught. From the definition of bn given in the theorem of Lorentz series, we have bn is equal to 1 by 2 pi I integral over c f of z by z minus z naught whole power minus n plus 1 into dz. Here if we put n is equal to 1, then what you will get is b1 is equal to 1 by 2 pi I integral over c f of z into dz. So this is the formula to find the residue of an analytic function. So residue of f of z at z is equal to z naught may be denoted by res of f of z comma z naught. This is the notation to denote the residue of a given function f of z at a particular point z is equal to z naught. And then evaluation of residue. First case, a residue of a pole of order m. If z is equal to z naught is a pole of order m, a simple formula to determine the residue is given by b1 is equal to 1 by m minus 1 factorial into limit z tends to z naught d power m minus 1 divided by d z power m minus 1 of z minus z naught whole power m into f of z. This is the formula to find the residue when the pole is of order m. Residue at a simple pole. If the pole is a simple pole, then the residue becomes uh, b1 is equal to limit z tends to z0, z minus z0 into f of z. That is, in the above formula, put m is equal to 1. Then what you will get is the residue becomes b1 is equal to 1 by 1 minus 1 factorial. It will become 0 factorial, that is 1. So 1 into limit z tends to z0 d power m minus 1 divided by d z power m minus 1. Here if we put m is equal to 1, then the differentiation become vanish. So what you will get is simply limit z tends to z0, z minus z0 whole power 1 into f of z. That is simply limit z tends to z0 into z minus z0 into f of z. Thus, if z is equal to z0 is a simple pole of f of z, then the residue of f of z comma z0 becomes limit z tends to z0, z minus z0 into f of z. And then third case, if z is equal to z0 is a simple pole of f of z, and if f of z is given as phi of z by psi of z, then the residue of f of z can be written as residue of f of z comma z0 is equal to phi of z0 divided by phi dash of z0. So this is the formula to evaluate the residue. And then Cauchy residue theorem. If f of z be analytic at all points inside and on a simple closed curve C, except for a finite number of isolated singularities, that is z1, z2, z3, etc., zn inside C, then integral over C f of z dz can be written as 2 pi I into sum of residues of f of z at z1, z2, z3, etc., zn. Note: if the singularities are poles, we can use the above formula to evaluate the residues of f of z. Otherwise, expand the function with the help of Lorentz series expansion and then find the residues. If f of z has a removable singularity at z0, then residue of f of z comma z0 becomes 0. Limit points of pole is a non-isolated essential singularity, and the limit points of 0 is called an isolated essential singularity. That's all. Thank you.